Moving on to the next question, we have a rectangle overlap, right? So for calculating this particular, like to see what is the actual problem, an axis, we are given list of 4 points. That is for one rectangle. For two rectangles, we have total of four another points. That means we have total 8 points. We need to check if that particular rectangle has some positive overlapped area or not. So if we just try to see, we are given a x coordinate system, xy coordinate system. There are two coordinates as in okay. So how are the four coordinates lined up? X1, y1 and x2, y2. X1, y1 is the coordinate of its bottom left. It's this the bottom left is present, and this is another present which is over here. Similarly, we have one over here and one over here. So this is 0, this is 1, this is 2, this is 3, this is 0, this is 1, this is 2, and this is 3. So we have this and we have another one like this, right? So it has some positive overlapped area, right? If, for example, in example 1, I'm discussing in example 1, the overlapped area is 2. Okay, so how can we calculate this? Now, the thing is, we need to focus on such coordinates like this coordinate, this coordinate, this coordinate, right? So, when can the positive area be formed, right? When can this possibility occur that a positive area is being formed or not? The positive area is being formed when there is a specific overlap of the width, right? Of the width or the height. There is some height. Uh, if there is a possible overlap, then that means that either the width of that particular overlap is positive or the height is positive. Any one of those, if all both of them should be positive in order to get a positive area, right? Suppose I give you another example. We have such type of rectangles, right? Possible. This would not have been a case of, uh, you know, it's not getting overlap. This is not a possible case of getting overlap. So for overlapping, there should be the width. This particular uh, x coordinate, I should say, should be lesser than this x coordinate which is present over here, or this x coordinate should be present over here. Either one of them, right? We can simply call it like if there are four coordinates such as given, so we can call it as this is a larger x coordinate, right? This is a larger x coordinate, and this is a smaller x coordinate, and this is a smaller x coordinate, right? So what should I say? That the minimum of the larger x coordinate, minimum of the larger x coordinate should be should be lesser than the maximum of the smaller x coordinates, right? We can just simply do. So if maximum of the smaller x coordinates, like this is present over here, this is present over here, and hence they're not able to get overlapped because L, that this is our final L, it is less than S. Like here it is upwards, here it is here. So as you can see over this particular condition, we are able to see that uh, yeah, you might have gotten an idea of it. So we try to just see return. There can be two possible conditions. Two possible conditions can be as if we talk about rec1, then there is 2, right? Then there is rec1, another coordinates for rec2, we'll have rec2 as well. So the minimum, the as you can see, I'm talking about this coordinate and this coordinate. I need to take the minimum of it. I need to take the minimum of it. Minimum should be lesser, lesser than what? Than what? The maximum of the smaller coordinates which are present, right? The smaller coordinates are 0 and another as 0, like 2. This is for width. Now we need to do the same thing for height as well. So for height, we have to have an AND operator first, AND operator, and then do the same thing for this. The only difference is that instead of rec1, the coordinate taking of coordinate of of taking coordinates as 2 and 0, we'll be focusing on coordinates 1 and 3, right? We can have 1 and 3 coordinates which can have such particular property. So talk about it, uh, width and height. This is 1, this is 1, this is 3, this is 3, and we can run. We can simply run it. Okay, so there's this problem which is happening, and return minimum of. Right. So the question says that we need to check if there's an overlapping required. So the overlapping will happen. Overlapping will generally happen when this is greater than the overlapping, because the condition for non-overlapping, we discussed the condition of non-overlapping, right? So this would just change it, and just change this sign, particular sign, and this will work. Let's just see if it works or not. Yeah, it does. So we can just move on to the next question, which is valid perfect square. Given a positive integer num, write a function which returns true if num is a perfect square, else false. Right. You know, we are not required to use any built-in library functions such as Sqrt. So we are given a number like 16, and we should return if it is a perfect square or not. So what are perfect squares? You know what are perfect squares like. If just if you just have if you just have it can the square root is a like it's a perfect integer, like it's an integer, so we're not required to use the sqrt library. So what are the methods that we can take care of, or we can think of while solving this particular question? So if you could just think of this question, I think that have one. If you're not required to use Sqrt, then this is a similar question which is being asked in the binary search as well. So it's a modified binary search. So if we have a take a look over that, you're assuming that int L is taken as 1 and int high is taken as none, right? So while L less than equal to H, we need to do something. We need to do something. So this becomes int mid is equal to L plus, to avoid overflow, we usually do like this. And what we try to do is int resultant integer like answer is actually the num divided by the mid value, right? And int remainder equals equals num modulo mid value. If our answer into if answer equal to mid value and remainder is equal to 0, we can clearly say that this is our function and we can clearly return mid. Else, if if our answer is greater than mid, then we can say that uh, low should be increased, value of mid should be increased. In order to increase the value, we try to else is equal to mid one. We try to increment the low value if in just in case the mid value is less. Here the mid value is less. If the mid value is greater, then we can simply say that hey, just answer less than mid, then we can just do it like this, and yeah, we can return false. We can return 2. We are required to return 2 over here, right? So that's it. We are following on basic binary search. We'll be discussing some questions related to binary search later. This is an overlog enough approach, and I think this should work. Okay, so it is not working because uh, Yeah, if answer is equal to mid, and then right, so what should be done? Basically I need to do this, right? I need to do this. Right, in order to do that, I think this should fine, because what, just in case if the answer is equal to mid but the remainder is not zero, then we should of course like we should just change any of those values, either this value or this value, everything will be fine. So I was just missing that particular test case. I think this would work, like when we are trying to solve more questions related to binary search. Also, like this should be less than, L is greater than, less than, equal to sign should be present. And now it's fine, like yeah, it should be working, because we'll be discussing about these particular cases, that why is this happening when we will be solving some questions related to binary search, right? So after that, we have a question as perfect number. Perfect number is a positive integer that is equal to the sum of positive divisors, excluding the number itself. Divisor of an integer x is an integer that can divide x evenly. So we need to have a perfect number, which is a positive integer that is equal to sum of its positive divisors. So we're required to find positive divisors of a particular function. So it's simple, it's quite simple. So what we'll try to do is int sum is equal to 0, right? For int I is equal to 1, I cross I is less than equal to num I plus plus, go until root of n and try to generate all those possible values that could occur, and I will keep a track of the sum, and we'll check if the sum matches the value or not. So that's it. So what I try to do is that if 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 num modulo I is equal to 0, then I could simply just say sum plus equal to I, and sum plus equal to num divided by I, and that's it. Uh, Also, I need to sum minus equal to that particular num, and then if sum equal to num, then I could simply say that hey, the number, we are satisfying that particular condition. We are returning true, else we should be returning false. That's it. Submitted. Let's see if it gets submitted for other numbers or not. For 1, we need to handle this particular case. So for 1, since 1 is an edge case, so the expected is false. So if 1, if num equal to 1, then it should be false, right? False. That's it. This was the entire thing we were thinking of. Let me see if it matches other test cases that could arise. Yeah, it's working. So this is one of the solutions. Another solution that they described was that was the optimal solution was based on the O of square root of n. Another was based on Euclid-Euler theorem. So it is a log n based approach. So when we try to explore log n based approach, when we will try to study Euclid's algorithm, this requires that particular thing. So maybe you should try to explain it on your own, but in this case, O of root of n solution is explained. So can we just have a look at the Euclid-Euler theorem, which is present over here? It is basically taking care of the Mersenne primes. So for 2 raised to power p minus 1 to be prime, it is necessary that p itself is prime. However, not all numbers of the form are prime. For example, this is not a prime number. You can see that for a small value of p, it's related. We need to evaluate perfect numbers for some primes, that is 2, 3, 5, 7, 13, 49, 31. And the thing is, for example, the first 4 perfect numbers are generated by the formula 2 raised to the power p minus 1 into 2 raised to the power p minus 1. Okay, so this is actually a perfect number, is a thing, is a real thing, which was proved by Euclid. and the representation is using this particular formula. You can just explore it. And so basically, if you just know that, like, maybe you might know of that particular thing, you might not be able to, not you might not have explored this particular theorem. It's completely fine. The optimal solution is, for this question I have coded, is in order of square root of n, and that's good. That's really good. That's fine to us. So let's move to the next question, which consists of valid boomerang. Given an array points where points I is equal to xi, yi coordinate system is given, represents a point on the xy plane, return two if these points are a boomerang. A boomerang is a set of 3 points that are all distinct and not in a straight line. Okay, so we are given an array points and a set of 3 points that are all distinct and not in a straight line. Okay, so that's a good question. Maybe it's a good question. What can we do is simply we can have the slope formula. It should have different slope, which means technically it means that it should have a different slope. So what can we do is, instead of points, we can have a dy for points. We can have dy, we can have dx at the same time. Dx, dy1, dx1. Let's try to do this. And int dx2 and dy2. X2 here, dx2, dy2, right? Now let's try to have all those values. So I'm assuming that we only have 3 points, right? Points over length is only 3, right? It's already given. So point, instead of point, I should write only p. I'm assuming that because confusion. P. So our first value is, for take 1. For dy1 it should be 1 minus p 0, it should be 1. 4, that's just it we're talking about. For dy2 it should be, instead of 1 and 0, it should be 2 and 1. We have done that. So this should be 0 minus p 0, 0, right? And instead of 1 0 for the same case, it should be as 2, and it should be 1. Later we just need to, dy1 by dx1 should not be equal to dy2 by dx2. So in other words, you can also write return dx2 multiplied by dy1 should not be equal to dy2 multiplied by dx1, right? That's it. You can just simply say that, yeah, this is not possible. Try to submit it. Yeah, it's fine. Uh, no, the slope should be different. We only took that. Since there are 3 points, we need to make sure that the slope generated by these 3 points, there will be 2 lines which will be generated, and the slope should be different. So yeah, that's it. And question. An ugly number is a positive number whose prime factors are limited to 2, 3, and 5. Given an integer, return true if n is an ugly number. So n is 6, 6 is 3, n is 8, 14, false, is 1, true. Okay, so I can see that in order to generate it, an ugly number is a positive integer, so there might be conditions like if n is less than equal to 0, I could simply return false. If n equal to 1, I could simply return true. Yeah. And I could just generalize on, and could just calculate for the rest of the values. So if I am able to see whose prime factors are limited to 2, 3, and 5, I could simply see that we first try to get all the factors of 2, we try to get all factors of 3, and we try to get all factors of 5. If we are able to see that is there any other number which is left, then we could simply say that no, we have reached, if the number is 1, if the number changes to 1, suppose let's just say that, so we have 2, 3 and 5. So ugly number would be 2 raised to power m, 3 raised to power n, 5 raised to the power k, something like that. If we try to remove all those values, we try to divide this particular number by this, try to remove this, and we could simply say that yeah, we have tried to remove all such values, and we can now just move on to the next next particular number. So what we'll do is while n modulo 2 equal to 0, n equal to 2, while n modulo 3 equal to 0, n 3, while n modulo 5 equal to 0, and to 5. Once this happens, we are convinced that all the factors of 2, 3 and 5 are removed, and hence if n equal to 1, then we simply say that yeah, so if it is 1, then we can clearly say that yeah, it was an ugly number. Otherwise, we could say that no, it still has some other factors which are present, and yeah, that's the question, and submitted. So yeah, we could just simply say that it was an easy question. So we have done this question. We have ugly number done, valid boomerang is also done, perfect number is done, square root of x is also done. Yeah, we can move on to the next question, that is factorial trailing zeros. It's a very easy question which was later discussed. So given an integer returns the number of trailing zeros in factorial. So the trailing zeros in factorial is basically it's a maths question. Okay, so it's a maths question. So if there is a particular factorial like 3, so let's just discuss about it. So we have 5 factorial. Let's just say for example, how does this 0 come? How does this 0 come? Like how is a 0 generated? A 0 is generated by using 5 cross 2, using 5 twos are 10, right? And if you could have some 5 into 4, you could generate another 20. If you could have 5 into 20, you could generate 100, right? So the crux point is, the basic point is that it should have a 5, right? It should have a 5. And since only 5 and 2 or powers of 5 or powers of 2 or like multiples of 5 or multiples of 4 or some other integers which have their factors as 2 or 5 contribute to it, we can just simply say that the number of 5 and 2 would basically mean that the number of zeros which are present, like since 5 twos are 10, it contributes to 1 0. One multiplication of 5 into 10 contributes to 1 0. If we had 5 into 20, that means 5 into 4 into 20, and 4 has two twos, so it contributes to two zeros, because 5 into 2 multiplications are, there are two in number, one of them is this and one of them is this. So that means the number of zeros is basically dependent on the number of 5 and 2 present. Now when we are trying to use a factorial, I would say the number of 2 factors will always be greater, since as you can see, like 6 factorial is present. Like let me just wipe this off. 6 factorial is present, like 6 into 5 into 4 into 3 into 2, right? This is a factor of 2, it consists of factor of 2, this consists of factor of 2, whereas 5 is like 5 has only one value. So the factors of 2 were in here, we had 2 into 3, we had 2 into 2, we had 2. So for any factorial n, we can say that the number of the number of factors as 2 will always be greater than the number of factors as 5. Hence, what is the bottleneck to calculate the number of zeros? The number of zeros dependent is clearly dependent on the number of fives, because number of twos is already in. They are very enough. They're very much present. They're very much enough. If you try to get some examples, you always see that the number of factors which are five are very less a number compared to the number of factors of two, because the same reason. So we have number of fives. So the question asks us to just calculate the number of fives which are present, right? So what can be done is we need to find the factors which are consist by the number of five. So how can we do that? It's very simple. It's like taking n and you're dividing it by the number of five, and then you are taking the same n and you're dividing it by something, some power of 5, and you're doing it so on. So how does this work? It works on the basis of like that there's a specific formula to calculate the number of fives which are present in a factorial. The calculation of number of fives is based on uh, it's a formula. So it's like int x equals to 5, int x equals to 5. So now what we try to do is while x modulo 5 equal to 0, or what should we say, while x is less than equal to n, that particular n variable, right? We try to do what? Int sum equals to 0. Sum will be returning the answer. Just the answer, right? While x is less than equal to n, we can simply say that uh, answer plus equal to n divided by x, value x, and then x, you multiply x by 5. So the next time it becomes 25. Okay. This entire the false condition fails, the while condition fails, and it comes out of the while loop. So this is a logarithmic based approach. For 5, what is happening? The output is 0. Okay, let me just see what is happening. So x is equal to 5 and x uh, plus equals 5. So x is equal to 5. So plus equals to n divided by x plus equal to plus. I was missing a plus, sorry about that. Yeah, it's working fine, and we can move on to the next question. So we have done this question. Now the next set of questions that we're looking for, I think we the number of questions which are present are 10 questions are left. So we'll try to solve all these 10 questions. So in this we have X kind deck of cards. We have Excel sheet column title. We have reverse integer. We have decode sort array, and we have these are bit manipulation based questions. So yeah,